Okay, welcome everybody to this week's Infosys Chandrasekhar and Random Geometry Colloquium. Today, we are very glad to have Bharath from Indian Institute of Science. We'll be giving a talk on an ergodic approach to an equidistribution result of Ferrero Washington. Over to you, Bharath.
Hi. Yeah, I don't know. Okay. Should I use this? Okay, I'll just work with the keyboard.
Oh, that's for the camera. Okay. But we okay.
This is fine.
Isn't it something? So this is the measure.
Okay, I can work with this. It's okay.
Sure.
Yeah.
Okay, I think let's start on this.
Yeah. Okay. Thanks for coming to the talk. So I'm a number theorist, so I don't know how to pitch a geometry talk. So I think it'll end up being very basic number theory and maybe very basic ergodic theory. Okay. So maybe before I talk about the main result is joint work with Jungwon Lee. And so maybe before I talk about this work, I just want to talk about one open question, which is of an ergodic flavor. Okay. Thank you. Yeah. So I just wanted to start off with maybe a sort of statistical question in number theory, which has nothing to do with my work, but I think it's sort of interesting nonetheless. So if you haven't seen these sort of prime numbers, I want to talk about irregular primes. And so the story starts with the Riemann zeta function, which is the summation 1 over m to the s. And so using calculus, you can show that it converges absolutely for real part of s larger than 1. And then using some complex analysis, you can show that it has an analytic continuation to the whole plane, except there's a simple pole at s equals 1. And so not only at positive real numbers, you can also make sense of it at negative integers or negative numbers. And in particular, number theorists like to compute these values at negative integers. And at negative integers, they have this very specific form given by Bernoulli numbers. So at negative integers minus n, it's given by this b n plus 1 over n plus 1. And then if you sort of unwind the definition, the odd Bernoulli numbers vanish. So the negative even integers, the Riemann zeta value vanishes, and at negative odd integers, they have this very specific form. So if you just write some down, zeta of minus 11 has this expression, zeta of minus 31 has this expression. And so I just want to point out that 691 is a prime number. It occurs as the numerator of zeta minus 11. Zeta minus 31 has this expression, and the prime numbers in the numerator are 37, 683, and this 3050, 65927. And so the reason number theorists like this sort of prime numbers is goes back to Kummer. And so what Kummer showed is that the prime numbers that appear here are what are called irregular primes. So again, if you've not seen what irregular primes are, you take a number field, which is q adjoin this complex number, which is a pth root of unity. It's exponential of 2 pi I over p. And so what one knows in algebraic number theory is that they're associated to number fields. There's something called the class group, which is a finite abelian group. And whatever it is, it measures the failure of unique factorization in this ring of integers z adjoin zeta p. Zeta p is this exponential of 2 pi I over p. And so this prime p, which I want to be R, is fixed. And what we do is that this class group, which is an abelian group, you can look at the p part of that class group, so the p primary part, something like z mod p square z or z mod p to the nz. And the definition of irregular and regular is that if this p part is trivial, then we call the prime regular, and if it's non-trivial, we call it irregular. And so the interest in number theory grew from this result of Kummer towards Fermat's last theorem, that if p is an odd regular prime, then Fermat's theorem for this exponent p is true. So x to the p plus y to the p equals z to the p has no non-trivial integer solutions. So then like this sort of interest in irregular primes grew. And although now we know Fermat's last theorem, and it's not like Fermat's last theorem had a solution for regular prime and then irregular prime, there was just like one solution. But the sort of result of Kummer led to independent interest in irregular primes. Okay, so I just wrote down some tables with some zeta values at negative odd integers. So if you look at some of the earlier ones, there's only 1 or -1 in the numerator. But zeta minus 11 has 691 as a factor, zeta minus 15 has 3617 as a factor. And then if you start writing down all these Bernoulli numbers, these zeta values, the numerators grow very, very quickly. So here are just some examples. So like 43867 is an irregular prime, 93847 is an irregular prime, and 37 is actually the smallest irregular prime, and it occurs in the numerator of zeta minus 31. Okay. Okay, so these are these irregular primes. So what's known? Is that there are infinitely many irregular primes. What's not known is are there infinitely many regular primes. Okay. What's known is there's some sort of periodicity. So I've given you these sort of prime numbers. I've given you these are some fractions. So there's a numerator, there's a denominator, and then you can just fix a prime and you can look at the mod p values of these rational numbers. Okay. So, I'm interested in zeta values and negative integers. So zeta minus 1, zeta minus 3, zeta minus 5, and so on and so forth. Zeta 4 minus p, and so on and so forth. There's some sort of cyclicity. After this, there's zeta 2 minus p, and then there is zeta minus p. But there are these Kummer congruences that say that the mod p values of them actually start repeating. Okay. But then you have these sort of p minus 3/2 values, mod p. And so this sort of naive heuristic that Siegel came up with is that you have these p minus 3/2 values and they are uniformly distributed. Okay, just a heuristic. And so if you believe Siegel's heuristic, okay, yeah. So if you just believe Siegel's heuristic, there are p minus 3/2 of these values. And I want to ask myself, when is a prime regular? So a prime is regular if p does not divide the numerator, p does not divide the numerator, p does not divide the numerator, and p does not divide the numerator. So the probability, is like 1/1 minus p that it doesn't divide the numerator. There are p minus 3/2 values. So it should not divide the numerator of all of them. And so as p goes to infinity, if you just do the calculus limit, it's e to the -1/2. And so the probability that prime is regular is e to the -1/2, which is like 60.65, and this is unknown. So we actually expect more regular primes, but it's not known that there are infinitely many regular primes. Okay, and in general, it could happen that p could divide two of these zeta values. So for 691, zeta of 1 minus 12 and zeta of 1 minus 200, p divides the numerator of these zeta values. And so I just want to state this question, which is not known in number theory. And if you just follow the same heuristic, you can fix an integer r. You can fix some index, and you can ask what is the probability that p divides r of those values, and then you expect some sort of Poisson distribution, and it's not known if that's true. Just data, yeah, just computational data, yeah. The square? Oh, I don't know the data. You mean the indexes too? Like 157 might also be something like this. Okay, but I don't know the data off the top of my head. Yeah.
Good experimental.
Yeah. So we know this. He made this conjecture based on evidence only. Yeah. Yeah. Okay. So yeah, I just wanted to say this result because I think it's a lot of fun, and it's just a number theoretic conjecture which has its roots from 1850, maybe number theory, and we still don't know the answer to this. But I want to talk about a field that's closer to my research interest. It's called Iwasawa theory. And there the sort of tagline is, instead of studying one number field, we want to study a family of number fields. So earlier on, I just fixed this one number field, Q zeta P, and I wanted to study the P class group of Q zeta P. But in Iwasawa theory, what we like to do is, okay, you look at Q zeta P square, Q zeta P cube, and so on and so forth, Q zeta P to the n, and you can look at all of them. And so you just take the union of all this Q zeta P to the n. That's this Q zeta P infinity. And instead of looking at the P class group of Q zeta P, P class group of Q zeta P square, and so on, I want to look at everything. So I want to look at the P primary part of the class group of Q zeta P to the n. And a slight technical point, which I think I might just sweep under the rug, is all of these class groups have an action of a Galois group, this Galois group of Q zeta P over Q. And in algebra, what you prove is that this Galois group of Q zeta P over Q is isomorphic to Z mod PZ cross. And so that's a cyclic group of order P minus 1. So long story short, like you have all these class groups and you have this action of the group, and so you can divide it into eigencomponents. Okay. So anyway, so this eigencomponent business is not going to be important for my talk, but I do have to state Ferrero Washington's results. So I will just keep this in mind. And so if you just sort of look at this eigencomponent A and I, it's just some P primary abelian group. It depends on n. So I'm looking at the nth layer here, and I'm looking at what the P. I'm asking myself what is this class group at the nth layer. And so what Iwasawa showed, and this was one of the first theorems that kickstarted Iwasawa theory, is that there's some sort of asymptotic formula for the size of the class group. So eventually, there's some sort of nice formula. So this class group is a P primary class group. So its size is a power of P. And so if you look at the exponent of P here, there's a linear term, there's a exponential term, and there's a constant term. So this linear term is this lambda invariant, this exponential term is this mu invariant, and then there's this constant term nu. So this lambda, mu, and nu are called Iwasawa invariants. And this result of Ferrero Washington that I was talking about is about this mu invariant. Okay. So this is this sort of famous result of Iwasawa that kickstarted Iwasawa theory. And when he had this result, he conjectured that this exponential term should vanish. And so this was a conjecture earlier on, and it's proved by Ferrero Washington, and another proof was later given by Warren Sinnott. So they showed that this mu invariant is 0 for this Q zeta P. And so I should say that Iwasawa's theorem was much more general. I sort of fixed a very, very specific sort of ZP extension, but his result is true, much more general, and his conjecture was also true for much more generality. But Ferrero Washington theorem is also known in a much general case. So I sort of fixed Q zeta P, but in number theory we can fix the same level. So I could look at n, big N P squared, big N P cube, and so on. So this big N is called the tame level, but I'll fix it to be 1 throughout my talk. Okay, so some technicalities aside. So I want to focus on this result of Ferrero Washington, who used some sort of ergodic theory to prove this result. And sorry, one slide of this will be commutative algebra. Apologize for that. And so the sort of result of Iwasawa, the sort of asymptotic formula essentially boils down to studying some sort of commutative algebra. And it's a commutative algebra over this power series ring ZP double brackets T. And so the idea that he had was, we had this Q zeta P to the N over Q zeta P. You can look at this Galois group, and you want to sort of package all this information together. And the way algebraists like to package information together is looking at this inverse limit. So you look at this group ring and you look at this inverse limit of the group rings. Okay, and so this isomorphism is given by just sending P plus 1 to some topological generator gamma. Okay, so there's some commutative algebra, and one of the famous results about this ring is this Weierstrass preparation theorem. So if you take any power series, there's some sort of factorization that you could do. This is a U of T, and you can write it, every element in this power series can be written as a power of P times a unit times this G of T. And this G of T turns out to be a polynomial. It's called a distinguished polynomial. And it's characterized by the fact that mod P, it's T raised to some power. Okay. So it's called a distinguished polynomial, and every coefficient except the leading coefficient is 0 mod P. Okay. And so this mu is this mu that appears here. And so the Iwasawa's result was sort of this lambda and mu invariance can be gleaned from something called the characteristic power series, some element in ZP double brackets T. And so if so somehow using commutative algebra, he was able to produce this power series called the characteristic power series. And the question of whether mu was positive or not reduces to showing that this mu is positive or not. And another way of phrasing is that P should divide every coefficient of this power series. That's equivalent to asking mu is positive. But then this sort of observation of Ferrero Washington was that you can look at this power series here, but you can also look at this power series as some sort of compatible family in this group ring. Okay. And so again, mu being positive just means that every coefficient is divisible by P. But then you can look at it in terms of this power series, or you can look at it in terms of this group ring. Okay, so that's it. So one of Ferrero Washington's and Iwasawa's first observation was mu is positive if every element of this you write it as a sequence of compatible elements, and you want all the coefficients to be divisible by P should mu be positive. Okay, so now before sort of moving on to this group ring, again, just some sort of basic combinatorics. So if you look at the p-adic ring, there is something called the p-adic expansion. So it's similar to the base P expansion. So every element in the p-adics can be written as this summation. So summation Ti P to the I. Okay, so it's like a base P expansion, except that the exponent of P is allowed to grow to infinity, and all of these digits T0, T1, T2, and so on, they belong to the set 0 up to P minus 1. So it's like a base P expansion, but instead of P, yeah, the only difference is that P is allowed to go to the exponent of P is allowed to go to infinity. And then once you have this p-adic expansion, you can look at the associated partial sum. So you can just truncate it at some nth level. That's this associated partial sum truncated at level P to the n minus 1. And then if you just divide by P to the n, you get an element of 0 to 1. Okay, so this is this sort of partial sum, and this is this normalized partial sum. Okay. Okay, so maybe one more algebra slide. So this Galois group of Q zeta P over Q, I told you was Z mod P Z cross. And in general, if you look at the Galois group of zeta P to the n over Q, it's Z mod P to the n Z cross. But this is a cyclic group of order P minus 1 times P to the n minus 1. And so you can write it as a P group times a cyclic group of order P minus 1. And so this cyclic group of order P minus 1 can be identified with this P minus first roots of unity. And this this cyclic group of order p to the n minus 1. These are the 1 units of Z mod p to the n z cross. So these are all the elements of Z mod p to the n z cross that are congruent to 1 mod p. Okay. And so the reason I was sort of emphasizing this group ring is because of this special element, the special theorem called the Stickelberger theorem, which has this very explicit form. So it has this very explicit form. It's a over p to the n, as a goes from 1 to p to the n, a co-prime to p times sigma a. So it's a very specific, very explicit element in this grouping. And the sort of Stickelberger theorem is that this element annihilates a certain. So I had this class group. I have this even components and odd components. The odd components together is what's called the minus part of the class group. And so this sort of Stickelberger theorem is that this very explicit element kills the minus part of the class group. Okay. And so again, this sort of theorem is very specific to Q, and it's not known even for other. Well, yeah, this sort of extension to other totally real fields is this thing called Brumer-Star conjecture. Okay. Anyway, so the sort of punchline is that I have explicit elements. These are called Stickelberger elements, and they annihilate this class group, minus part of the class group. Okay, so this was this criteria of Iwasawa. That okay, so I want to ask myself, when is mu positive? But they had this very specific criteria using the Stickelberger element. So if you go back to the specific form of the Stickelberger element, I wrote it as a sum as A varies in Z mod P to the NZ cross. But Z mod P to the NZ cross can be written as some elements in this delta, which is this P minus first roots of unity, and some elements in this Gn. So when you break it up in that way, it's a little bit more complicated. But if you follow your notes, if you just write down these things here, the partial sums that come up, the partial sums that I wrote down in the previous slide come up in the expansion. Okay. So anyway, so the partial sums come up, and if you look at the partial sums, these are defined using these digits T1, T0, T2, and so on and so forth. Okay. So again, if you just follow your notes, mu being positive just means that you want all the coefficients to be divisible by p. And so this is what Ferrero Washington observed, is if you just use that criteria, it just boils down to taking a sum over the p minus first roots of unity and looking at this very specific sum being congruent to 0 mod p. Okay, so it's a sum over this p minus first roots of unity. This eta is this some factor, eta to the d, and this sort of Tn alpha eta is sort of these digits that appear. Okay, so somehow this mu being positive, which is some sort of Iwasawa theoretic question, just boils down to studying digits of p-adic numbers.
What is Tn?
So alpha eta is a p-adic integer, and Tn is you look at the p-adic expansion, Tn is the coefficient of p to the n. Tn is just the thing that appears in front of p to the n. Okay, yeah, so mu being positive is just almost a criteria that doesn't depend on anything, and it's just a yeah, it's almost feels like a very independent criteria, independent of the setup. Okay, the only one condition that I sort of want to sweep under the rug is this: I'm only looking at the minus part, and the sort of restriction to the minus part comes from something called the reflection theorem. So, yeah. Okay. Okay. So now I'll try to make it ergodic, but maybe it might be too simple. Okay. So the question is about this p minus first roots of unity. I'm looking at some summation that only involves this p minus first roots of unity. Okay, and this each term involves these digits. Okay, so the sort of axiomatic setup is instead of looking at p minus first roots of unity, let me just fix some arbitrary collection of p-adic numbers, beta 1, beta 2 up to beta r. And the only condition that I want to put is that they are linearly independent over q. So there's no q linear combination that maps to 0. And the sort of main result, so to show that mu is positive, you have to show that something like this is true. There exists an odd integer such that for all n and for all alpha belonging to ZP, this condition holds. But we know that we want to show that mu is 0. So it's enough to show some alpha and some n for which this condition doesn't hold. So this is a very, very strong criteria, and somehow you want to use ergodic theory to prove that this strong criteria doesn't hold. And so what Ferrero Washington show is they prove an equidistribution result. They prove an equidistribution result in 0, 1 to the r. And so what the sort of stuff set up is you just take r linearly independent things in ZP, and you look at these partial sums in 0, 1 to the r that I just described. So you look at beta 1 up to beta r. You want to look at the set of all alpha in ZP. So this GR is the set of all alpha in ZP, such that this partial sum Sn minus 1 alpha beta 1 over p to the n, so on and so forth, Sn minus 1 over p to the n of alpha beta r. So this is in 0, 1, this is in 0, 1. So I have r things in 0, 1 to the, I have r things in 0, 1. And so the set of all alpha says that this r tuple is equidistributed as n goes to infinity, is the set GR. And the main result is that GR has full Haar measure in ZP. Okay, so I have this subset of ZP, it's a collection of all alpha says that this tuple is equidistributed in 0, 1 to the r. And so the main result is that this has full Haar measure in ZP. And so they apply this proposition to a linearly independent set of p minus first roots of unity. And again, this sort of, they have this very explicit elements, and they just use the Weyl criteria to show that this set is equidistributed. And so we sort of just want to try to use an ergodic approach to reprove this result. Yeah, so you have to do a little bit more work, but that's a lot of algebraic trickery, I think. Yeah, so they have this ergodic result, and it's not super straightforward to go to that result, but if I look at the proof, it looks a lot of algebraic manipulation, so I couldn't find anything more philosophical for that. So we just focused on this equidistribution statement. Okay, yeah, so the idea is to sort of try to give an ergodic proof. And so we want to use Bernoulli shifts. And so maybe some preliminaries if you haven't seen ergodic theory. So if you start with a compact topological space, and if you have a measure that's a probability measure, so mu of x is just 1, and it's a measure on the Borel sigma algebra. So a sequence in this space is said to be equidistributed if you take any continuous function f, then the average of that function over xn. So you fix a big M, and then you take the average from 1 to m. As m goes to infinity, you want this average to converge to the integral of f. So I guess with respect to nu, yes, yeah. With respect to 8, yeah. So yeah, I might actually, yeah. No, I really don't know measure theory, so I might actually make a lot of such errors. Yeah, so I guess the tagline that helped me keep track of things was, equidistribution is a property that involves interplay between topology and measure theory. Okay, so the statement of Weyl criteria is that, okay, in general, you can do it for any function, or you need to show this for every function, but the Weyl criteria for 0, 1 is that you don't have to show it for every function, you have to just show it for a special class of function called test functions. And the test functions, in the case of Weyl criteria, are these exponential functions. So you just have to take every non-zero vector in z to the r, and then you just look at the exponential of xn, the dot product of 2 pi I b. And so you can show that the integral of this exponential is 0. And so the Weyl criteria is just that you just have to take these test functions. So yeah, so their form was explicit enough that they could use the Weyl criteria. But the sort of approach that we want to just consider is if you have a dynamical system, which is just a tuple, this x, mu, and this along with a self map, that's a measurable map with respect to nu. This measure is a t-invariant measure. That just means that the measure of a measurable set is the same as the measure of its inverse image. And a map is said to be ergodic if you take if it satisfies the following property. If you have a measurable set with the property that its inverse image is B itself, then it has to be either the whole thing or an empty thing, or measure theoretically it has to be the measure of B has to be 1, or the measure of B has to be 0. And a point is said to be generic for this map or for this dynamical system if the orbit of the point is equidistributed in the previous definition. Okay, so yeah, maybe to keep myself grounded itself, this example helps me a lot. So if you have an irrational number, using the Weyl criteria, you can show that if you look at the sequence n alpha, that's equidistributed in 0, 1. But if you can also look at the rotation by alpha map, so you can take x to x plus alpha. And I guess in ergodic theory, this is what's called a uniquely ergodic map. So the Borel measure is the only thing that works for this system to be ergodic. But when you have this sort of setup, every point turns out to be generic. So the orbit of every point is equidistributed. And so if you just look at the orbit of any point, it's x plus n alpha. And then if you just work backwards, if you look at the orbit of 0, you get back n alpha. And so this sort of approach tells you that n alpha is equidistributed as n goes infinity. Sorry? Yes. R equals no, this is just this is a different thing. Yeah, this is I don't know any ergodic theory, and this is the first sort of principle to convince you that this sort of approach is useful. So Ferrero Washington proved an equidistribution statement using Weyl criteria, and we want to do something using ergodic theory. And so the question is, why should something like this work?
If you just do 0, 1,
yeah. No. No, yeah. Okay, yeah, I'll talk about it a little bit. Yeah, I'm just saying that this is a completely different setup. It's just to say that this ergodic approach is useful. So this sort of statement is equivalent to the fact that n alpha is equidistributed. But this n alpha has nothing to do, there's no prime involved there, it's just n alpha. Yeah. And just saying that, this ergodic maps in general need not be uniquely ergodic. And so in general, not every point has to be a generic point. But then you have this sort of following theorem in ergodic theory that if you have an ergodic map, almost every point is a generic point. So if you have this sort of dynamical system and this T is ergodic, then if you look at the set of all points, is that X is a generic point, that's set as measure of 1. And so in general, if you give me a point, figuring out whether it's a generic or not might be hard. But if you have this sort of generics, this general statement, then it might be a little easier to use this theorem. And our main motivation is that there have been instances, notably of Konu and Matsal, who've used some very powerful tools in ergodic theory called Katnos theorems to obtain results in Iwasawa theory. And so we wanted to see if this result of Ferrero Washington can also be obtained using ergodic principles. Yes, yeah. So something like this is what we end up using anyway. Okay. Okay, so the sort of ergodic tool in our approach is what's called Bernoulli shifts. So if you just have a finite set of alphabets, A1 to AN, And if you have a probability vector, so you just have a vector v1 up to vn between 0, 1, with the property that the sum of these vi's sum up to 1. So this vector p defines a probability measure on this finite set. But also you can look at this Bernoulli scheme, which is this Cartesian product a to the z or a to the n. And you can equip it with the product topology and the product measure. So you get this Borel sigma algebra. And then there's this sort of dynamical system that you can define. So, if you have this sort of sequence of alphabets, you can shift everything to the left. So left shift. So it's shifting everything to the left. But even if you have a one-sided sequence, you can just forget the first thing. So you can shift everything to the left. So you have a two-sided Bernoulli shift and a one-sided Bernoulli shift. And so instead of, I want to consider this not just for one, I want to consider this sort of R-fold product. So I have this sort of R-fold dynamical system. And so again, one of the theorems in ergodic theory is that this R-fold ergodic system is ergodic. Okay. And so again, so maybe here I just want to point out that
Supply shift each of the.
separately, yeah, just separately. Yeah. And just to contrast this with this rotation, if you just take a twofold product of the rotation by alpha, then that's not ergodic. So already this Bernoulli shift is way more powerful. Okay, so the thing that we want to apply this Bernoulli shift business to is just this finite alphabet space 0 to p minus 1. So these digits. And this probability vector that I want to look at is just this uniform probability vector 1 over p. And then if you just look at ZP, and if you look at every element in ZP has this unique p-adic expansion a n p to the n. But if you just follow your notes, this alphabet space to the n is actually isomorphic to ZP as topological spaces as measurable spaces. Okay. And then we have the shift map that I want to look at. And so the shift map, you can also think of it in ZP. And so a p-adic number is called normal if it's a generic point for the shift map. And then in general, if you have an R tuple of p-adic numbers is called jointly normal if it's a generic point for this R-fold product T to the R. Okay. And maybe, yeah, so we have this p-adic numbers, but you can also think of PRE numbers. So yeah, so I wrote down summation a n p to the n. But you can also think of like PRE numbers a n over p to the n. After all, I'm just interested in digits. So you can either think of it in ZP or in 0, 1. So you can look at the base P expansion and you can look at the map that's multiplication by P. So the multiplication by P map is also going to shift digits. And so this map is also ergodic, and yeah, it can also be viewed as a shift map by considering this expansions in base P. And again, it's just a property of digits. So this generic points of this multiplication by P map are also called normal numbers. And as far as I know, if I understand it correctly, it might be possible to artificially construct some normal numbers. Rational numbers are not normal numbers. But if you just in general give me an irrational number, I think it's hard to figure out if it's normal or not. And one of the folklore conjecture is that if you give me an algebraic but irrational number, then it's normal. And I don't even know if there's a single algebraic irrational number that's proven to be normal. Okay, someone told me this, so okay, yeah. So I don't even know if there are examples of algebraic irrational numbers that are normal. So one of the sort of folklore thing that I heard from Ralph is this. What they showed was this tuple in 0, 1 to the R. So the main result is to show that this tuple is equidistributed. But it's only for when they introduce this parameter alpha, the set of alpha says that this tuple is equidistributed, has full Haar measure. But earlier on, you have this p minus first roots of unity. Those are some algebraic numbers that are not rational. So initially they didn't think of adding these alphas, and they just wanted to prove that this thing is, this tuple is equidistributed without introducing this alpha. And they were just stuck. And I think Ralph heard this talk, he's my advisor. And he's like, okay, why don't you try to introduce this parameter alpha? And then the next day, Larry Washington proved it, apparently. My advisor like does not know ergodic theories. So this is just to like tie up with the previous point where it seemed like an approach. You just have this p minus first roots of unity. Those are algebraic irrational numbers. Try to prove things are normal or jointly normal, and that didn't work. But you can still like prove some Iwasawa theoretic results. Okay. Okay. So the sort of main observation, at least from my perspective, and I think this is sort of the punchline of our work, is you have ZP and you have 0, 1. You have this p-adic expansion and you have this p-adic expansion, and you have this map that goes from the p-adic expansion to the p-adic expansion. So you have summation an p to the n to an over p to the n plus 1. You have this usual topology and measure here. You have this usual Borel measure here, the topology there. And the sort of magic that sort of works for us is that this map is continuous and surjective. The opposite map is not that good. Okay. So this map is like, so every number integer actually has a unique p-adic expansion, but that's not true for that's not true for base p expansions. You have rational numbers of the form a over p to the n, and they have two base p expansions. So you can look at p minus 1, p minus 1, p minus 1, p minus 1, so on. And in general, you don't have to go from p to p. If you go from the two-adic expansion to this base 3 expansion, and you just factor out this 2, then you get the image gives you the Cantor set. Okay. Okay. So yeah. So somehow in our picture, we want to look at both the p-adic side and the real side. So we want to look at the p-adic extension of the of 0, 1, or we want to look at the p-adic extension of the circle, which is just a ZP cross R mod Z. So this sort of p-adic extension is what's called the p-adic solenoid. And so one way of looking at it is just ZP cross R mod Z. But then if you want to change this lattice Z, so Z is just diagonally embedded inside ZP cross R. So X just goes to X comma minus X. But another way of looking at this, you can upgrade this ZP to QP. So it's this fraction field of ZP. And then the lattice that you then choose is a Z 1 over P. And so this is just a group. You can add things, addition. So it's a cube with a Haar measure. It's also a compact space, so you can give it a probability. You can normalize the Haar measure so that it's a probability measure. And this sort of, just like this modular curve, you have this choice of fundamental domain, and it's just a simple domain ZP cross 0, 1. And so just like in the modular curve case, this fundamental domain surjects onto this p-adic solenoid, and it's a homeomorphism outside the boundary. So it's just a homeomorphism outside the boundary, which is ZP cross 0, 1. And so this fundamental domain also has this measure. So this is the Haar measure on ZP, and this is this Borel measure on 0, 1. Yeah. So the sort of map that I'm interested in is a shift map. But then I have this space 0, 1, this alphabet space 0 to p minus 1 to the Z. But that maps to this fundamental domain ZP cross 0, 1. And the way this works is that if you have this, if you have A0, A1, and so on and so forth, you can map it to the p-adic expansion. And if you have these elements, these digits with negative indices, you can look at the base p expansion. So this part out here gives you the p-adic number. This part out here just gives you a number from 0 to 1. And again, if you just follow your nose, you have the Haar measure here, you have this Borel measure here, and then you have this Bernoulli measure here. That's going to come from this uniform probability vector 1 over p, 1 over p, 1 over p, and so on. Okay. Okay. So okay. So I told you that I have this sort of map that I like on this alphabet space 0, 1 up to p minus 1 to the Z. That's this two-sided shift. But what does it translate to in this p-adic solenoid? So there's actually a very simple description in the p-adic solenoid. It's just a multiplication by 1 over p. Okay, so this is, we just like to call it the Hecke map, because it's just introducing some denominators p. And then you can again follow your nose and you can ask what is the map in this fundamental domain. So there you have to play a little bit, but again, there's a very explicit formula. Yes, yeah. So yeah, the p-adic solenoid is also, yeah, you have this inverse limit of the z s1s. Yeah, that's also a p-adic solenoid. Yes. Yeah. So another way of looking at the p-adic solenoid is you have this R mod z, but then you have this multiplication by p map, and so you just look at the inverse limit like that. Yeah. So once you have this inverse limit, then there's also another way of looking at this. But yeah, again, you have this sort of skew map here, which if you have this p-adic number, you can. It basically means you want to shift the digits. So you just forget the first digit and then you just divide by p. But then you have to like carry this forward onto the real side. So then you have y plus t naught of x divided by p. Okay, so you have all these maps, and it's essentially coming from this two-sided shift. Yeah, so you have this two-sided shift on the alphabet space. You have this explicit skew product on this fundamental domain. And then you have this sort of Hecke map coming, that's this multiplication by 1 over p on this p-adic solenoid. And all this, you have this commutative diagram here. Okay, but what's also true is that if you have zp cross 0, 1 to the r, you have this projection onto the zp factor. And then if you look at what the map does on the zp factor, it's just this one-sided shift. Okay. And so the first set of, again, very silly observation is that I want to characterize generic points for the two-sided shift. So I want to characterize those generic points for this, what appears in this fundamental domain. But the sort of main point is that you have a map on both ZP and 0, 1, but it only depends on the ZP component. So you have this sort of R tuple, where each element of the tuple is a p-adic number and a real number. You have this R tuple in ZP cross 0, 1 to the R, and I want to ask myself, when is it a generic point for this product? But the sort of statement is that if you have, if you just look at the ZP component, so this huge complicated mess in ZP cross 0, 1 to the R is a generic point, if and only if the mess in the ZP part, so gamma 1 up to gamma R, is a generic point for the one-sided shift. And sort of intuitively, the idea is that it's a left shift. So so you can eventually move everything to the left side. So if you want a pattern here, it will come from a pattern here, because eventually you will move the pattern from here to here. But everything here is just a ZP component. So it's just a vague idea of explaining things, but it's just to say that everything only depends on the ZP component, and you can make the vague thing that I said precise. Okay, so yeah, so that's one observation. And so if you just apply it to this point where this real component is 0, and so if you keep applying this two-sided shift, what you see is that this normalized partial sums appear. So you subtract the first digit, second digit, third digit, and so on, and then divide by p to the n. But then you have to carry it over to the real side. Then this normalized partial sum appears. This normalized partial sum appears. And so the point is that if you have this tuple gamma 1 0, gamma 2 0, gamma r 0, and that's a generic point for the two-sided shift. So it's a generic point in this ZP cross 0, 1 to the R. But then you have this continuous projection, ZP cross 0, 1 to the R to 0, 1 to the R. The push forward measure is actually just a Borel measure here. And so if you have this sequence that's equidistributed in ZP cross 0, 1 to the R. So if it's equidistributed here, then its projection will also be equidistributed in 0, 1 to the R. Where the projection is basically this this R tuple of normalized sums that Ferrero Washington were interested in. So somehow you start with this two-sided shift, and I want to study genericity there, and I can get genericity here. So this is sort of punchline is you want to transfer information from the p-adic side to the real side. Okay. So this is the one observation, and the second observation is we have this general little r case, and I want to reduce to the r equals 1 case. So I just want to reduce to the r equals 1 case, and somehow at some point I have to use the fact that the beta i's that I had were linearly independent. Yeah. So the reduction step is the following. Again, I can only look at the ZP side. So I have gamma 1 up to gamma r. And I want to ask myself, when is it a generic point for the R-fold Bernoulli shift? So you can take a vector m that's non-zero. So m is just a vector in z to the r. So if you have a vector in z to the r, if you have this R4 product, you can project it down and get an element in this one. Just this is one copy, and then in this one copy, you can look at the Bernoulli shift, which is this multiplication by 1 over p. But taking the dot product and multiplying by 1 over p is the same as multiplying by 1 over p and taking the dot product. So this diagram commutes. And so basically what we show is that, so if you have a generic point here, then it projects onto a generic point here, but the converse is also true. So the gamma I is now in the solenoid, yes, yeah. So this, this R4 product is this here. Okay. Yeah. So the point is you can reduce from the general R to the R equals 1 case by looking at all these linear combinations. Okay. Yeah. So now the Ferrero Washington theorem that I stated can actually be proven if you combine this proposition that involves this reduction step from general R to R equals 1, and this sort of proposition that you don't have to look at both the real part and the p-adic part. You can only look at the p-adic part. Yeah. So the Ferrero Washington theorem can now be proven using whatever we know about the general R case. And so this linear independent of the beta i's comes in when we apply the second proposition. And the fact is, I had the statement about full Haar measure, and I also had the statement about Z linear combinations. So I have this. So I had this vector m in Z to the R, all elements in Z to the R except the zero vector, and Z to the R is a countable set. And so what happens in proving this full measure is that you have to take this countable intersection of full measure sets, but then a countable intersection of full measure sets also has full measure. So that's useful also again from when you go from this general R to the R equals 1 step. But this reduction step for us was purely group theoretic, and we didn't really use any complicated machinery. It was things Stone-Weierstrass at best. So we didn't use any explicit analysis. So somehow what this seemed to suggest is this ergodic nature of the problem is if you can somehow in general just focus on the R equals 1 case, that might be enough. Okay. So this is one final remark, and so again, yeah, so Ferrero Washington have already proved the results. So our main motivation was maybe just to understand some ergodic theory, and then finally to look at some sort of generalizations. And so the sort of generalizations that would be interesting is, are there any generalizations that you can look at? Sort of like this, the previous case that I was looking at was the circle, and are there any GL2 generalizations? And so if you're interested in number theory, we have this Iwasawa's conjecture, and our case, the base field was Q. But what if you change the base field to a real quadratic field? I think not much is known about these mu invariants there for real quadratic fields. But the other sort of GL2 generalization is instead of characters, we can look at elliptic curves and modular forms. And in this case, the Stickelberger element also there's an analog of the Stickelberger element. And these are using what's called modular symbols. Okay. And this analog of Iwasawa's criteria actually goes back to the thesis of Hira's student, Haesung Sun. And so, yeah, so there's an analog of this Iwasawa's criteria that I wrote down. And then you can ask if there's an analog of this Ferrero Washington equidistribution statement. And I think there's no statement that's known to be true, except that there are conjectures of Maser, Rubin, and Stein. Some uniform distribution conjectures of them. Okay, so this uniform distribution conjecture was, I think they said it in their talks. I think there was like some preprint, and now they have this. Okay, so so their conjecture is the following. So it's not an equidistribution result. It's a some sort of statistical distribution result. So if you take a modular form, there's something called a modular symbol that you can associate it to it. And then, if you have a modular form, you can integrate something like this. And so what they do is they integrate between, say, epsilon infinity and a over n. And then you can normalize it so that if you fix a prime number, then this is in Z localized at P. Okay. So let me now make this denominator like P to the n. So as you increase fractions, so you can look at this mod P value of these elements as you only look at these fractions with P power denominators. So it could either be 0 mod P, 1 mod P, P minus 1 mod P, and their conjecture. So they stated a conjecture that as you let n go to infinity, the probability that it takes x mod P is 1 over P. The probability that these values is x mod P for some fixed x is 1 over P. Yes, yeah. So so that's their conjecture, and they had a bunch of conjectures, and so they had this preprint or maybe paper, arithmetic statistics related to modular symbols, but I think this conjecture doesn't appear there. But they had, yeah. Yeah, so I guess you can look at the geodesic from on the upper half plane. You can look at the geodesic from infinity to a over P to the n. So it's just a vertical line. Yeah, so I mean, this could a priori be like some random complex number, but you have to normalize it so that it's algebraic. And so this depends on, like, if it's an elliptic curve, then it will depend on this elliptic curve. Yes. So, but then if you see, there's a very precise conjecture, but average versions of these conjectures have been proven by Petridis-Risager and Lee Sun. So this is Jungwon Lee and Haesung Sun. And so I think the sort of tagline is that Petridis-Risager used some spectral methods or automorphic methods, which I don't know. So this work of Lee and Sun, they just use dynamics of continued fractions. So the sort of connection to topological dynamics is very. It's an inventionist paper, and I think the tagline is modular symbols have normal distribution. yeah, I don't think I can say anything about either of their works, except that I know Jungwon and Hisang, I think they use continued fractions. And so the main thing that we wanted to also highlight was, continued fractions have this sort of symbolic dynamics associated to them, and so that's what we wanted to highlight in the GL1 situation with this p-adic digits. And so this relationship between continued fractions and this symbolic coding of geodesics on the modular curve, it goes back to a lot of authors, and I think one of the substantial results in this area is by Bowen and series. And so what we wanted to explore is, there are more ergodic tools to study this geodesics, and this sort of work we wanted to look at p-adic extensions. So if you have like a p-adic extension, like do we have p-adic extensions of continued fractions that can be explained using this sort of geometry? Yeah. Thank you. Yeah. 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 I've tried. I don't know. Okay.
So you get authority.
Okay. Yeah. 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 So our first result, what we wanted to do was look at lattices inside like SL2R cross SL2QP, which comes from this gamma naught n or gamma naught. There's one over introducing this denominator, but I don't know how to make this work, which is why I mentioned this continued fractions, this p-adic extension of continued fractions, which I also don't know, but thank you.